Physics from West Virginia University, where his thesis was involved with mass power studies and nickel molybdenum alumina catalysts. He also has a PhD in physics from University of West Virginia University. His thesis work for that degree was in EXAFS studies and the structural properties in small metal particles. He is experienced as research associate at West Virginia University and presently with the University of Kentucky Consortium for Fossil Fuel Liquefaction Science. His talk today is on the development of binary ferrihydrite catalysts for direct coal liquefaction. Dr. Zhao.
The consortium of fossil fuel liquefaction is a research group supported by DOE, and it consists of scientists from 5 universities: University of Kentucky, University of Utah, University of Pittsburgh, and University of West Virginia University, and Auburn University. And Jerry Hoffman is the director of the consortium. In the past 8 years, the scientists in the consortium have made great effort to develop a new catalyst for direct coal liquefaction. What we are looking for is a low-cost, and disposable, and effective catalyst. And low cost means probably $1 per kilogram is the price which is economically feasible. So we have no choice but iron. As we can all understand, if the catalyst is highly dispersed with a large surface area with small particle size, probably we can increase the activity to decrease the loading. Since the catalyst, iron catalyst we are talking about usually is the catalyst precursor, and during reaction it converts to pyrrhotite. So we hope there's no agglomeration under the reaction conditions, and active means it's a high oil yield and total conversion. We start this work on a commercial catalyst. This is a commercial catalyst by Mark I Incorporation. It was first introduced by Dr. Bert Davis to a consortium, and the catalyst has been extensively tested by the people in the Energy Center of the University of Kentucky. And this is manufactured using a patent technology and was originally defined as a hematite. Very small particle size, 30 angstrom, and large surface area. Was originally used for enhancing the combustion rate of rocket fuel. And it's a reddish brown, free flow powder, and absorb a lot of water. But water is really bad for the activity. The price is very high, over $500 per kilogram. But it is very interesting material. So what I like to do is the following. First, we will discuss the structure of the catalyst, and then we will discuss the mechanism of water absorbed at surface on agglomeration and phase transition. And then, what is the effect of chemisorption impurity at the surface on agglomeration and phase transition? And I will show you the co-liquefaction results. And also, we discuss the related catalyst. It's impregnated with iron catalyst, the phase, and the conclusion. Now we know this catalyst is not really a new material. This is a material people call ferrihydrite by geologists. And ferrihydrite is considered to be one of the 8 major iron oxide hydroxides. And those are the familiar fields like hematite, hemimite, and magnetite, and goethite. These are familiar fields. The ferrihydrite is number 8. And there are many structures proposed. You can look at the formulas. So it's really people don't know what is the actual structure of this material. And this material can be easily prepared. And if you put a ferric nitrate solution and add ammonia, you will see reddish brown precipitate. And this is ferrihydrite. And if you look at the procedure, it really don't cost $500 to do that. Now, so what is the difference? Probably you will ask, what's the difference between the material produced by this method and the method used by Mark I? And I will discuss it later. And this is the material usually used for precursor for the formation of goethite and hematite. And it's good absorbent and used as a catalyst. And for example, this is one of the reaction I found in the literature. And of course, it's a very low cost material for liquefaction. But in the literature, in catalysis, people usually don't call it ferrihydrite. People call it amorphous FeOOH. When you use X-ray absorption fine structure, we find the structure of a ferrihydrite or sodium angstrom catalyst is not that complicated. In fact, if we divide the material into two parts, the bulk part, the iron is surrounded by 6 oxygen and OH groups. But the surface is different. The iron has a tetrahedral symmetry. And if the catalyst is properly dried, and then it will lose one bond and becomes surface, becomes coordination and saturate. And we published the result last year on Journal Catalysts. And the catalysts also show some interesting results. For example, I mentioned this is a precursor for hematite. It means if I heat the catalyst, it will lose water and convert to hematite. Now, if I compare the TGA curve of the ferrihydrite to alpha FeOOH, and you will see there's a sharp transition at around 250 degrees for alpha FeOOH. It means around 250 degrees, and all the alpha FeOOH converts to hematite by losing weight of water. But you don't see a clear-cut phase transition for the ferrihydrite. So why? We annealed the sample at different temperature, and then we took a picture, electron micros picture for the catalyst. And these are the annealing results and the microscope. And at 250, 300, 350, and 400. At 250, you see two phases. These are the ferrihydrite particles. And there are some larger particles. These are alpha Fe2O3 hematite. If you increase the temperature, you will see more hematite. And also, the particle size of hematite becomes larger and larger. But the interesting part is you see both phases coexisting. This is unusual because this is single phase material. While during annealing, after annealing, you will see two phases. But if you recall, so why? If you recall the structure model, probably the explanation is very simple. Here, look at our structure model. Suppose we have two particles. We call particle A, particle B. Now, this is the surface coordination and saturated site. And if there's water there, then the water will link these two particles to form a particle cluster. And at high temperature, the water probably will be evolved from particle joint. and then the particle will agglomerate. And finally, it will convert to hematite. In other words, if we have some particles here, these are ferrihydrite particles. On the surface, they have dissolved the water, and this water will link the small particles. And then at high temperature, maybe 250 degrees, and these four particles will agglomerate and converts to hematite. But those particles will remain as ferrihydrite. So this is our explanation. And it is very easy to prove whether this explanation is correct or wrong. If we have two samples, one is dried sample. One sample, we purposely let it exposed in air for 10 days, for example. Then we will expect the air-exposed sample will have more water molecule absorbed at surface. And then we are near the sample in the same condition and look at TEM picture. Now, this is the result. And if you compare it with, these are in same condition. The top is the moisture air-exposed ferrihydrite. And this one is the dried one. And you certainly see more hematite larger particles formed. And if you look at most bulk, give a better result. And on top, this is a ferrihydrite measured at 12K. This is after annealing at 250 C, and you see there are basically two phases. One is the red one is ferrihydrite, and these sharp peaks represent hematite. But if the sample has been exposed to air, you will see more hematite form. And the fitting results tells us if it's a fresh sample, hematite is only 35 to 4%. And if after air exposure, and the hematite increased to 73%. So it means water is really accelerate the formation, agglomeration, and the formation and of hematite, and resulting in the loss of surface area. So let's look at the model again. This is the structural model for ferrihydrite. Now with water, maybe we can say these sites become the crystal growth site. On the other hand, if we put some impurity ions in the solution, probably this site will absorb the impurity ions instead of water. And then we can block the crystal growth site. So we try to add something impurity to the solution, precipitation solution. And what we got is we call binary ferrihydrite. The bulk part is ferrihydrite, but the surface is absorbed with impurity ions. And we successfully put silica, alumina, moly, phosphorus, zinc, and organic ions at the surface. So let's see what the surface can do to prevent the agglomeration. On left is pure ferrihydrite. This is for ferrihydrite, two broad peaks. If I anneal the sample at 225 C, you will start to see hematite. If I increase the temperature, you see more hematite. And at 300 C, you see hematite only. This is a pure ferrihydrite. Now, if I add silica or aluminum to the precipitation solution, silica at 425 C, you don't see any phase change. And you increase the temperature to 450 C, and then you see the formation of hematite. Alumina is not as good as silica because you see but still the transition temperature increased from 225 C to 275 C. Why? Why silica is better? And from the structure model we can understand, because silica likes tetrahedral size, and iron likes octahedral size. So if you have a two particle, and when the surface is covered by silica, and these two particles cannot agglomerate. But on the other hand, alumina likes octahedral symmetry. So alumina probably is not as good as silica in terms of preventing the agglomeration and phase transition from ferrihydrite to hematite. So it means the catalyst, the binary ferrihydrite catalyst, is able to maintain its dispersion at high temperature. So probably it is better catalyst. So we did the liquefaction test. And basically, it's analyzed by extraction method, and the result is separated into two parts. One is we call oil and gas, and another part is S14 and pre-S14. We test. This is a thermal reaction. This is ferrihydrite without secondary impurity ionize. And this is the 30 angstrom commercial one. And this is with silica. And this is with citric acid treat catalyst. On top is for bland canning coal, and there is a black blend of coal. And you can see consistent improvement of the oil yield. Also, the total yield. These two is we call 2,2 yield. And 2,2 yield is better than the thermal reaction. And we also checked the pyritide phase, because the active phase is pyritide. We put the catalyst into the reactor, but we didn't add any coal, and we checked the phase, the pyritide phase after reaction. And this is what we see. If it's pure ferrihydrite, this is a commercial 30 angstrom catalyst. After reaction, you see very nice crystals. Pretty, but this is not what we want to have. And if with silica dispersion, we see very nice better dispersion of the pyritide phase. So it means by adding silica to ferrihydrite, the catalyst can maintain its dispersion and preventing agglomeration and forming a high surface pyritide phase, which is more active for co-liquefaction. Now, I want to move on to discuss another method used in liquefaction. Basically, I think there are two approaches for co-liquefaction. The one I just talked about is I call conventional approach. Usually, we synthesize a solid state catalyst, and then we add catalyst with coal, or we mix it with coal and before reaction. And there's other method called maybe we can call it unconventional method. Usually it's sometimes called impregnation catalyst on coal, or iron exchange iron catalyst. And the catalyst in this method, catalyst is usually formed with the presence of coal. Usually, okay, I will discuss later. And so the question is, what is the active phase of this method, and why the catalyst is active? Here I want to discuss the method, the impregnation method. Impregnation method, I think this is Dr. Gibbons. And Dr. Gibbons studied this method 10 years ago, and recently it is further developed by the scientists at PETC, Pittsburgh Energy Center. The method is quite simple. First, they mix the coal with ferric nitrate solution, and then make a paste, and then put the paste to an ammonia hydroxide solution, and then wash and filtration with vacuum pump, and then dry. And they found this method is much better compared to another method they call physically mixed catalyst, which means, like just I mentioned, first you prepare the ferric nitrate solution and then put ammonia hydroxide to the solution and get the precipitate, and then get the ferrihydrite catalyst, and then mix it with coal and react with it in a reactor. And Houdini found this method is better. And why? And he says, because this method, the catalyst is intimidate contact with the coal and maintains a fine particle size upon conversion to the active sulfide phase. So what Houdini says is this model. He says, in fact, he used the method. The full name of the method is called incipient wetness impregnation precipitation method. And this is a method people use for support catalysts. So what he says is the following. If you use this method, then you will have ferrihydrite impregnated at the surface of coal. If you simply mix the ferrihydrite catalyst to coal, then you have less contact between the catalyst and the coal. So you can think probably this is better. But here's the catch. Why? Don't forget the surface area of coal. If coal has 100 meters per gram, probably you will have this one. But what's the surface area of coal? Probably it's only 1 meter per gram. If a simple calculation will show you, you will not have this kind of impregnation. Instead, you will have something like that, right? Because there's no surface area for this kind of impregnation. So, and if you look at these two methods, probably not much difference because all the ferrihydrite particle doesn't have contact with coal. So these two should be very similar. Why this method is better? I think the explanation is simple. Now, if you put coal in solution, inevitably some ions will be dissolved in the solution. These are green ions. Could be organic or inorganic ions. And these ions, when you put ammonia hydroxide to the solution, and then you will have ferrihydrite. And this impurity ions will deposit at surface, absorb at surface. So basically, this mesh will produce binary ferrihydrite catalyst similar as the catalyst we mentioned. So probably it is the case, but to convince you, but this is not enough. We need physical evidence. First, we have to prove the iron phase formed indeed is ferrihydrite. Secondly, we have to prove the surface is different. Surface is absorbed with impurity ions. We have to have physical proof of that. Also, we should say prove the DCl activity of this material binary ferrihydrite catalyst is as good as the impregnated catalyst. Fortunately, we can do that. We can prove that. So first, I have to give a brief introduction of a phenomenon called superparamagnetism for small iron particles. There's a relaxation, because particles are so small, there's a relaxation time. And the relaxation time is defined as a function of Kd divided by Kd T. Here, K is the magnetic and isotropic energy, and it depends on the shape of the particle, and stress of the particle, and the surface of the particle. And V is the volume, and T is the temperature. And tau 0 and Kd are the constants. Now, if tau is less than the time scale for the instrument, then we will see a paramagnetic spectrum. But if it's great, then we will see magnetic spectrum. Now, if tau equals to the tau for the instrument, then we will see a complex intermediate spectrum. And we define this temperature as TB, and we call it blocking temperature. And blocking temperature is, if I convert this equation, and I can get this equation, and these are constants. So the blocking temperature is proportional to K, which is the magnetic and isotropic energy and the volume. And first, I'll give you an example. This is a nickel particle, 40 angstrom nickel particle, and measured at different temperatures by Topsol and Marot. The left is the particle in vacuum, and 70, and this is typical for paramagnetic spectrum. And then if we lower the temperature, passing the blocking temperature, we will see 6-line pattern. And the 6th line is the magnetic spectrum. And from this spectrum, you can see the blocking temperature is about 25 K. But if the surface is absorbed with hydrogen, and then you see the blocking temperature drop to about 16 K. In order to see the effect of surface, and so it's purely due to the surface absorption. So in order to see the effect of surface and isotropic energy on superparamagnetism, there are two conditions have to be satisfied. First, we have to have a very small particle size. Because if you have small particle size, then you have light diffraction of surface. And then second, the surface has to allow chemisorption. Fortunately, we have both. We have 30 angstrom, and we have cast site at the surface. Now, here I'd like to show you first, this is pure ferrihydrite or 30 angstrom catalyst. In the blocking temperature, you see at around 75, you see a complex spectrum. And below 75, you see 6 line. So we say the blocking temperature is about 70 degrees K. Now, on the right is a ferrihydrite treated with citric acid. It means there are organic ions absorbed at the surface. And see what happens. You see blocking temperature drop to 30 K. You see, it's 50 K, 50 if you compare these two, you see the difference. And blocking temperature is about 30 K. So here is the effect of surface. Now let's look at the impregnated catalyst. It's an impregnated catalyst using Kugini's recipe. If you compare these two, there's a slight difference. You see another phase here, the red one. In fact, this is iron phase in coke. Coke contains iron. But otherwise, it's very similar. And you can see the blocking temperature for the impregnated catalyst is about 35 K. Compare very close to 30 K for the ferrihydrite treated with citric acid. So this gives us direct evidence is the impregnated catalyst is really absorbed by impurity ions. And these impurity ions prevent particle agglomeration. So the catalyst can maintain its dispersion and become more active. And the result can be achieved by the catalyst we call binary ferrihydrite catalyst. But in the above, I compare the result of our catalysts to two different kind of catalysts. The first one is 30 angstrom catalyst. The second one is impregnated catalyst. And here I make a comparison table. The active phase for 30 angstrom is ferrihydrite, but we have binary ferrihydrite. They use the flame synthesis. We use iron pentacarbonyl, and we use precipitation and use ferric nitrate. The particle size are about the same. Bulk density is the only difference. You see, the bulk density means if I just measure the density without pressing the powder. This is very light, 0.1 gram per cubic centimeter. Our sample is 10 times of that. And why? If you look at the TM picture, it's clear. If you look at TM, this is the ferrihydrite we prepared. You can see all the particles stick together and form a kind of more particle aggregate. And the 30 angstrom is well dispersed. Why these particles always stick together? Water, right? Because they are water absorbed and at the particle surface, and this water link the small particles to form a particles cluster. And this is the only difference between these two catalysts, and between $500 and $1. And we check the ECL direct cold liquefaction activity. We found our catalyst is better. And the price, I just mentioned, this one is $500. Of course, it's nobody can use this catalyst. And our catalyst probably is $1, even less. Now, we compare the catalyst we prepare with the impregnated catalyst. The active phase, I have shown you, both are finally ferrihydrite oxide, because this the iron phase surface, iron ferrihydrite surface is covered by impurities. What is in for the impregnated catalyst, we don't know. But here we can control. We can put all kinds of second elements at the surface. In preparation, they both use, first they put ferric coal to ferric nitrate solution. So suppose the catalyst loading is 1%, and we want to liquefy 100 kilogram of coal. Then you have to add 100 kilogram of coal in order to produce 1 kilogram of catalyst. But in our case, we just put some secondary element, and this is we need for 100 kilogram of coal. For 1 kilogram of catalyst, we need 50 gram of impurity ionides, and we achieve same goal. And if you think about difference between 100 kilogram and 50 gram, the saving here is enormous. And activity we found probably is about same. The price, this is of course much lower. And in addition, as you can see, this catalyst has more controllable parameters. Probably we still don't have the best catalyst. But if we can somehow vary the surface composition, probably we'll have a better active and selective catalyst. What I just talked about is unsupported catalyst, but I think probably the result may help us understand some phenomena for supported catalyst. First, for supported catalyst, people don't ask this question: why the catalyst can be impregnated on support? People don't ask. But if you think of the structure model I just present, because the ferrihydrite use the impregnation method, the ferrihydrite has some vacancy, has surface. So the ferrihydrite, the small iron oxide particle, can be easily attached at the surface of support. So what kind of nature, probably we have better understanding. And another one is why the activity of a catalyst depends on support. I think Professor Carmen Bettmuller raised this question. He said, why you have iron catalysts on silica and aluminum, but the activity are different? Now, use the impregnation method, the incipient wetness impregnation method. Inevitably, there are some silica ions will be dissolved in the solution. And these silica ions can be solved at the surface of the iron oxide surface. And if you look at the surface for the aluminum oxide iron catalyst, this is the iron oxide particle. And is covered by aluminum. So of course these two are different. And another question is, people find why the reducibility of iron catalysts is depending on the loading of iron. Well, how we can explain like this. If you increase the loading, because the amount of silica ions dissolved in the solution is limited. We have only certain amount of silica. So if you increase the loading, certainly you will decrease the coverage of silica at the surface of iron oxide. So the surface becomes less protected. And in this case, if here, I mean, the iron load in this case is 2 times of that one. So in this case, probably the catalyst can be relatively easy to be reduced. So if you increase the loading of iron, then the reducibility should increase too. And this is true. Here is the data by Topsu, and he summarized the data from 12 publications. And this is the iron loading, and this is the reducibility. And you see, if you increase the iron loading, then the reducibility certainly increases. To summarize my talk, and I'd like to show you the structure model I showed you before, because we really like this model. And we use this model, we explain many interesting phenomena. We use this model, we explain why water is bad for the catalyst. And we explain why can-solve impurity will improve the dispersion. And also, we show you, in fact, this new catalyst is better. And also, we show, in fact, that this catalyst is identical to the impregnated iron catalyst. And finally, I'd like to take the opportunity to say something. Thanks for the people at the University of Kentucky Center for their assistance with the various experiments. Thank you.
And we have time for questions.
Yes.
You talked about the impurities that are being deposited on your iron
Yeah.
parts. Don't those impurities though change the catalytic properties?
In what way? So we think probably somehow vary the surface.
Isn't it even possible that you could put materials there that would even enhance the activity?
Yes, sure. So we like to test.
You'd like to
There are
be
so
able to
many.
do that, right?
Ah,
Like to be able to do that.
yeah, should be able to. There are so many choices.
Yeah, right.
When you speak of the materials being 30 angstroms and yet free flowing, is that in a dry state?
That's
Which
right.
obviously that must be not the individual particles, but clumps of particles that are
You cannot.
free flowing. Is that right?
No, it's an individual particles, I think. So that's why you can free fly, because they use this flame synthesis.
Yeah.
Probably, one drop of the liquid contains only one particle, so this particle will not contact this other particle, and water is not there. That's why.
Yeah. Well, I was thinking of it as the powder.
Yeah.
Normally things that are that small diameter are cohesive in that they behave like a flower,
Yeah.
but they don't want to flow. But this does flow.
Yeah, it does flow.
Well, I find that pretty much different than I would expect.
So the answer is really small. It contains probably about 2,000 atoms.
Yeah.
Thank you.